In this video we will consider cooling systems. So before we looked at heat engines, so a big gray circle in the middle that said heat engine. This time let's look at a refrigerator. So first question, what direction should the arrows go in? Well, with a refrigerator we have a cold side and a hot side. If your refrigerator is working well, then the inside of your refrigerator should be colder than the outside of the refrigerator. So this is your room, and this is inside the fridge. If the refrigerator is working right, the whole idea of a refrigerator is to take the cold side and make it cold. So you actually have to remove heat from the cold side to have a working refrigerator. So you're taking heat out of the cold side. What about work? Does the refrigerator do physical work? No, it doesn't do anything like that. In fact, you have to plug it into the wall, and so it takes energy, electrical energy. There's a pump underneath the thing that actually does work to make this happen. So work is not coming out as it would with a heat engine. Work's actually going in. Alright, so we've got work going in, we've got heat coming from the inside of the refrigerator. If it's coming in here and coming in there, it can't come in from there, then the heat would just build up inside. It needs to flow back out. So the arrow here has to be going up. So now it says we're taking heat and putting it out into the hot side. And if you've ever touched, it's usually the back of the refrigerator, sometimes it's the side of the refrigerator, occasionally it's the bottom of the refrigerator. It gets very hot while it's running. So that heat is coming out of the refrigerator into the room. So that's what you're seeing there, is that heat. So now if you open it up and look at it, you can see the work going in, you can see the cold going in, and the hot coming out. So if I look at efficiency, efficiency is what you want. That's this. How much of what you put in went where you wanted it to go? Well, if I'm putting in work here, and what I want is this coming out of there, it doesn't actually make sense because none of the work that I'm putting in is actually doing what I want it to do down here. The work is all going out as heat, but in that process it's also pulling heat out of here. So this is not some fraction of the work. It's actually coming from somewhere else. So in a case like this, we don't have a real efficiency. What we have is a coefficient of performance. So the coefficient of performance is what you want. In this case, that's QC, divided by what you put in. You put in the work to make that happen. Alright, so the equation for the COP would be different for a refrigerator that's used to keep food cold and for a heat pump that's being used to heat a building. The building that I'm in, Muntz at Blue Ash, is actually heated by a heat pump. A heat pump doesn't have like a gas flame in it like a furnace would to heat the air in the room. What it does is actually exchanges heat with groundwater. It's often used because it's a more efficient way of heating and cooling than having a furnace and air conditioner. The COP for a refrigerator, that's what we want, which is we want the cold part coming out of the cold, that was QC, over what we had to put in, that was the work. Now for a heat pump, what you're trying to do is make the warm part inside the building warmer. So you run this in the winter to keep the inside warm. So what you actually want is the QH. So that's what it does when it's colder outside than inside and you're trying to keep the inside warm. Which one also works for an air conditioner? An air conditioner, the idea is the inside air you want to be colder than the outside air. So it should be cooler inside the house than outside. So inside your house, that's where the TC is. Outside would be TH. And what you're trying to do is pull heat out of TC. So what you want there is the QC. So COP for a refrigerator would be the same as for an air conditioner.